exactly. Much closer to now. Yeah, three, I think. All right, let's get started. So let's go over the answer real quick. It's actually a lot more simple than you think. I see a lot of you. Thank you, Sammy. Time's up. I see a lot of you guys attempting to do crazy integrals. Remember, Gauss's law is to prevent you from having to do integrals at all. If I drew my Gaussian surface, just like that, right? I have this charged surface, all right? Let's say it's infinitely large. It doesn't really matter. My point P, my point P is located on this surface at the top here. And if I were to use Gauss's law, I would say that if I have some closed surface, then the area times the electric field times the area of that closed surface should give me the charge inside divided by epsilon naught. So the electric field, which is what I'm looking for, it's starting to do that thing again. The electric field multiplied by the area of my Gaussian surface. So what is the area of my Gaussian surface? It's the cylinder that has these two surfaces, top and bottom, right? What angle are those in terms of its normal and its and the electric field? It's not 90. The cylinder is, but the surface is 0 degrees because the normal is pointing upwards. The electric field is pointing upwards. So I have my 2 times the area of those things. So 2 times pi r squared, because there's 2 surfaces, one at the top, one at the bottom. What about the sides of this cylinder here? What angle are they at? They're at 90 degrees. So what is the electric flux through those? 0. So there's no flux through the sides of the cylinder. So I don't even write those ones down. That's equal to the charge inside divided by epsilon naught. And the charge inside here, right? Because I'm taking it for this Gaussian surface, so only that part of my my plate is contributing to this. And so that part, if I were to look at the Q, oh my goodness. If I were to look at the Q there, it would be equal to sigma multiplied by the area of that little area, right? So pi r squared. So now I'm left with E is equal to 2. Oh my goodness, this is annoying. 2 pi r squared is equal to sigma times pi r squared over epsilon naught. Pi r squared cancel. E is equal to sigma over 2 epsilon. Okay? Are we okay with that? Okay. That's for one plate. All right. So if I were to draw this plate here, if I were to draw this plate over here, and this has a positive charge, then the electric field lines are going to go up and down because it's thin. Now let me ask you guys a question. In this expression, the one that we derived, E is equal to sigma over 2 epsilon, is the distance, how far you are from the plate, is it relevant? It's actually not relevant, all right? As long as you're not so far away that your infinite surface doesn't look like an infinite surface anymore. So like if I was an ant, right, and a really tiny microorganism, and I was standing on this table is humongous, right? So this is basically an infinite flat surface for a microbe. But for us, it's not an infinite surface. If you were to look at this table from the moon, what would it look like? Point charge. It would look like a point charge. And therefore, you would treat it as a point charge, and you can use kq over r squared. In this case, if we're close enough to it, whether we're right here or right here, the electric field is about the same, so we can use Gauss's law to make that approximation. So I can say that the electric field here is also the same. Correct or not? Okay, good. If I were to draw now a negatively charged plate here, and I did the same exact thing, so this one is negatively charged, and I drew the electric field lines, well, the electric field lines are going to go inward. That. And this is looking familiar because you guys have seen this in the video last class. Like that, all right? And what do you notice about the electric field above the top plate and below the bottom plate? Yeah, so this is canceling each other out, this is canceling each other out, right? And therefore we are left with 2 times the electric field of one plate, right? Because the electric field of the positive plate goes in the same direction as the electric field of the negative plate in the middle. So therefore you can add their electric fields together. So the electric field on the inside, what would it be equal to? 2 times sigma over 2 epsilon, which is just sigma over epsilon, okay? So for parallel plates, E is equal to sigma over epsilon, okay? Now this question wasn't hard once you knew what to do, right? The math was super duper easy. The hard part was figuring out what's the right Gaussian surface, knowing what to do. The math of it was actually really easy. So would you consider this to be a hard problem or an easy problem? Easy. It's easy once you know what to do. I can say the exact same thing about every single problem on the test next week, okay? They're not harder than this. They might be a little bit more complicated mathematically, but they're not harder than this. All right, so you guys can definitely do it. Just don't get caught up in doing these crazy, ridiculous things. Okay? This is a great segue because today we're talking about capacitors, and capacitors, in essence, are parallel plates. And there's an electric field in those parallel plates equal to sigma over epsilon. Are we good? Okay. So if you look at the board here, on the left, you'll see a capacitor. And a capacitor is something that you'll see in a lot of different things. Your camera flashes are capacitors. Your defibrillators at a hospital, that's a capacitor. Things that, you guys know what surge protectors are? Surge protector. It's like those big blocks that you plug in computers at home to, like the big computers, to protect them from surges. Those things are made of capacitors. Your power supplies for your computers, for your laptops and your phones, those all have capacitors. And the reason you have that is to protect your devices so that you don't suffer from sudden loss of energy. Okay, so if you have something plugged into the wall and all of a sudden the light goes out because of some electrical storm, then a capacitors are they exist inside your devices so that they can continue giving energy to your computer so that it can shut down properly before any damage is done. Okay? That's why, let's say if you hard shut down your computer, you could do a document recovery. It's due to capacitors, all right? We actually owe a lot to capacitors. So that's what we're going to talk about today, how to talk about capacitors. You guys know who this guy is? No. Who said no? So he's holding a kite in a lightning storm. Literally the most famous electricity person in the world. Who? Not Newton. He's on a dollar bill in the US. It's Franklin. All right, this guy is Benjamin Franklin. Yeesh. He discovered capacitors, but he never described them, right? So he actually unknowingly discovered capacitors. The person who described them is this man here, Faraday. Do you guys, is his name ring a bell for you guys? What's that? A Farad. What's that? Yeah, okay. But Benjamin Franklin, that's the one you see in all the cartoons when you're a kid. He's getting shocked by lightning. Um, not in French. Yeah. Who's more famous in French? Vasco da Gama. No, he's Italian. Who's a really Alexander Graham Bell? Yeah, I guess so. Is he French? I okay. Uh, now Faraday described capacitors, And he named the units of how good a capacitor is after himself, which is called a farad. And so the units for capacitance, just ignore those little blips there. There's really nothing I can do. If you can't read it, just let me know. So units for capacitance are farads. And the symbol for that is F. Like what? Like force? And that's a Fahrenheit, maybe? So yeah, okay, so capacitors, what they do is very special, okay? Capacitors, table at the back, please shut up. Thank you. Capacitors, what they do is they store charge, okay? So if you give it a current, the charge will go inside, and it'll actually stay there for a long time, actually even longer than batteries. They're described by two parallel plates, just exactly like what we described. The electric field in between is just how we calculate it. It's important that they're parallel plates because otherwise this doesn't work at all. They're separated by distance d, and they have an area that's going to be important. And the thing that's going to be new to you guys today is there's substance in between the two parallel plates. That stuff is called a dielectric. Okay, that's right here. That's a dielectric, and a dielectric has to be an insulator. A really good insulator is a really good dielectric. A really poor insulator or a conductor is a terrible dielectric, right? And we'll talk about why that is. Any questions about this? A couple of seconds to write that. Yeah. Say that again. Made. Oh, any insulating material. So ceramic, wool, paper, glass. In this diagram? Oh, I don't know. It's just blue in this. It's just representing a material. It's depending if you have a circular capacitor, most of the time you want a malleable substance. So it'll most of the time be something like what's that stuff called there? Fiberglass. Yeah. All right. So here's the definition of what a capacitor is. A capacitor has something called capacitance. And capacitance is how well it holds a charge. So a really good capacitor will hold the charge better than a really crappy capacitor. And you can calculate the amount of charge that it can hold, Q, by relating its capacitance to the voltage applied to it. All right? And if you really need another relationship to make this a lot more obvious, if you rearrange this equation, so you made it Q is equal to C over V, right? Is that right? Nope, wrong direction, sorry. Q over V is equal to C, so I sent the V at the bottom there. You can think of it as how much charge per volt the capacitor can hold. And that's what capacitance is. Capacitance is the amount of charge per volt that a capacitor can hold. You increase the voltage. Does that make sense? Yeah, exactly. You increase the voltage, you decrease the capacitance. Okay? Now, if I have a capacitor, and the capacitor is already made, does the capacitance stay constant regardless of voltage? So a capacitor is how well it can hold a charge. So by changing the voltage, am I changing how well it can hold a charge? No. So if voltage, if I have this relationship here, if I have this relationship on the right here, Q over V is equal to C, if voltage goes down, then what needs to happen to the charge? The opposite? It goes down. Yeah. So if this goes down because C has to remain constant. C does not change, is not dependent on charge and is not dependent on voltage. Okay. And here at the bottom, we saw this already, right? So the electric field of a capacitor or parallel plates is equal to the charge divided by epsilon alpha, epsilon area. And what's charge divided by area? You guys remember? It's just sigma. So in fact, it's E is equal to sigma over epsilon. That's how we saw it earlier today. Yeah. Depending on each other. Exactly. But how do you make a better capacitor? So you have a capacitor. Now, how do you want to make that capacitor? How do you want to make it better? Well, then there is this equation here. All right. So how do you make a capacitor better? Well, there's many different things that go into what determines something's capacitance. One is the area of the plates, right? If I increase the area, I increase the capacitance. If I decrease the distance between the two, then I also increase the capacitance, right? So if I make my plates much larger and bring them really, really close together, then my capacitance should go up. Okay, that makes sense. And then there's this K. This is not the same K as Coulomb's law. That's not the same K as in Coulomb's law. This K represents that dielectric material. Okay, it's what we call material permittivity. Duh, didn't you guys know that? So basically, this is a multiplier. It's got no units. Okay, it's kind of like index of refraction. You guys remember that? Or coefficient of friction. You guys remember that? Okay, so it's got no units. It's just a multiplier. The higher the K, the higher the capacitance. And K is a measure of how good an insulator something is. So the better the insulator, the more charge the capacitor can hold per volt. So far, so good? Okay. So I got a video to show you guys. Now this morning I tried to do this and the sound played some weird tricks on me. So bear with me if I can hopefully figure this out. I can't remember which video it is. I believe it's this one. Sorry.
As long as those three things are true, then we can represent.
Ah! Sorry, Maxime, what'd you say? Okay. So it sounds like you guys know about this guy already. He's really, really, really good. He's one of the people that I recommended you guys watch stuff on YouTube. Sam, you actually looked at some of the other guys that I talked about. Michel Van Biezen is also very good. They're all very good. You should watch them.
Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 30. It's on the electric field of parallel plates. And we've already learned so far that the electric field will look like this. It'll go from the positive to the negative, but we haven't got into the details of that. Before we get there, let me give you a quick application of this. In biology, we use gel electrophoresis. And what you do is create an electric field across this gel, and then you can add DNA fragments to it. So we're going to put DNA fragments in right here. And what happens is they'll respond to that electric field. And DNA has a negative charge, and so
Sorry, I don't know what's going on. How do I get rid of this?
What they're going to do is they're going to migrate across.
How do I get rid of this? Normally you just swipe away and it goes away. Okay.
Hi, it's Mr. Anderson, and this is AP Physics Essentials Video 30. It's on the electric field of parallel plates. And we've already learned so far that the electric field will look like this. It'll go from the positive to the negative, but we haven't got into the details of that. Before we get there, let me give you a quick application of this. In biology, we use gel electrophoresis. And what you do is create an electric field across this gel, and then you can add DNA fragments to it. So we're going to put DNA fragments in right here. And what happens is they'll respond to that electric field. And DNA has a negative charge, and so what they're going to do is they're going to migrate across that electric field. Now what's interesting is the DNA is each going to have a different size, and so the small fragments will be able to move really, really far, and the larger fragments won't move as far. And so we can create a DNA fingerprint. And so if we have two parallel plates, and we make sure that they're oppositely charged, and we also make sure that that charge is uniformly distributed, and we also make sure that we're really far from the edge, as long as those three things are true, then we can represent the electric field like this. And if that's our electric field, we know that the electric field strength is going to act perpendicular to those plates, and it's also going to be constant or uniform throughout. In other words, no matter where you test the electric field inside here, it's going to give you the same value. It's going to be the same direction, and it's always going to be the same size. Now, how do you figure out the electric field strength here? There's a couple of ways we could do it. We could look at the voltage across that gap, and then the displacement, or R, across the gap, and that would tell us the electric field strength. Or we could just use the charge of the plates and the area of those individual plates, and that's going to give us the electric field strength as well. The last thing you should pick up from this video is what happens if we add a charged particle to this electric field. What happens if I take a proton, for example, and I give it a velocity in the horizontal right here? Can you predict what's going to happen as it enters into the electric field? Remember, positive charges are going to follow the electric field, and so watch what happens as we let it go. So it bends like that, but you can see that it continues to have the same velocity in the horizontal. What we're really doing is changing it in the vertical. And so this works exactly like projectile motion. However, projectile motion, that electric field is going to be the gravitational field. So can you predict what will happen if I take a negative charge and add it in that direction? Which way do you think it's going to go? And like that. It looks just like throwing a baseball, that parabolic curve, because it's the same thing. It's moving horizontally, and that's not affected by that change in the force in the vertical. So in order to look at the electric field of parallel plates, it's sometimes easier to look at them individually. So if we look at the positive plate and we draw the electric field lines, it's going to look like that. It's all moving out from the plate. And now if we draw the negative, it's going to be moving towards the plate. And so if I now simply just combine those two, it's going to look like this. Now you can see on the edge, in order to figure out which way they're going, we'd have to do some vector addition. And so we're just going to say that we're really far from the edge. And then you can also see up here and down here that that net electric field, since it's so close together in relation to the overall length of this plate, that it's also a net of zero. The only place where they're going in the same direction is going to be in the middle. And so we can treat that as our net electric field, that uniform electric field on the inside. And if we want to figure out what the electric field strength is, we could use the charge and the area of those plates. And so if we use this equation, what we've got here is the electric field strength is equal to Q, which is going to be the charge, divided by the permittivity of free space. Remember, that is a constant, and so that's going to offer resistance to an electric field. and then we're going to multiply that times area. And so if we increase the charge on the top, then we're going to increase the electric field strength. And if we decrease the area, then we're going to increase electric field strength. So let me kind of walk you through that in a PHET simulation. We've got here our two plates, and we can add charge to that. And the charge will show up right here, and then we can measure the electric field down below. And so what we're looking at is what happens when we increase Q, and then what happens when we increase or change A. And so what we're going to do is put our electric field sensor right in the middle, so you can see there's no electric field strength, and as we add charge to it, watch what happens to our electric field. It's getting greater. And so what we could do is at this point we could solve for E. If I add more charge, or I add more of the negative charge, you can see I'm increasing that electric field strength. Now what happens if we change the plate area? As we decrease the plate area, you can see that we're increasing the electric field strength. Because it's in the denominator, if we decrease it, we increase the electric field strength. If we increase the area, what we're doing is decreasing the electric field strength. And so it's a really nice relationship between charge and the area of the plates and then the electric field strength. But we could also go at it in a different direction. We could look at the voltage or the potential across that gap and then the distance or the displacement between the two. Now voltage, remember, is the amount of work that we would have to do to move a positive charge against that electric field. So that's going to be the voltage. And then R is going to represent the displacement or the distance between those two plates. And so here is our equation. Again, if we increase the voltage, we're going to increase the electric field. And if we decrease that displacement, we're going to increase the electric field as well. And so we've got another little simulation right here. So what I've done is I've got the electric field sensor in the middle, and now we've got a voltmeter. And so now as I add voltage, I'm increasing the volts. Watch what happens to my electric field. So an increase in the voltage as we move it up to 1.5 volts is going to increase that electric field. And we could move it in the opposite direction, and we're going to have the same thing. The more voltage you have, the more potential difference you have, then the greater that electric field strength is. But watch what happens when we decrease the distance between the two. So as we make it closer and closer together, we're increasing the electric field. Since R is in the denominator, by decreasing it, we're actually increasing the electric field strength. Last thing you really have to understand is how motion of particles inside an electric field is similar to motion of objects on our planet. So imagine I were to roll a ball across a table, and at the moment it goes off the edge of the table, we take a similar ball and we drop it from a similar height. You've maybe done this before. Which one's going to hit the ground first? Well, the right answer is that they're both going to hit the ground at the same time. And the reason why is that they're both in a gravitational field. And so even though this one is moving horizontally, that doesn't affect the force and therefore the acceleration in the vertical. They're both going to fall at the same rate. Now, charged particles work the same way inside an electric field. And so if this is our electric field, what happens if we add a positive charge to it? It's going to follow those electric field lines. But what happens if we shoot a positive, let's say a proton, horizontally into the electric field? It's just like that ball rolling off the table. It's going to accelerate down at the same rate as that point charge did to begin with. Or if we add a negative charge, and that negative charge we shoot into the electric field like this, it's going to do not what balls do on our planet. It's going to actually go against the field. And that's what's cool about electromagnetism. It's going to go in that direction. But it's still following this similar path as projectile motion because we have this set electric field. And so did you learn to create representations of the electric field between parallel plates? Again, we have to be far enough from the edge and the plates have to be close enough together. Did you learn to calculate the magnitude and determine the direction of the field? Again, we could use voltage and displacement or separation, or we could use charge and area. And then finally, did you learn to represent the motion of electrically charged particles inside an electric field, similar to that of projectile motion? I hope so, and I hope that was helpful.
Okay, so I showed you that because I wanted you to see the relationship between the electric field and the strength of the electric field when you decrease the distances between them. That's what I wanted you to get from this. The rest of the stuff we had kind of already seen before, so I wasn't too worried. I have more videos to show you later. I just want to move on from this. All right. All right, so here we have what a capacitor might look like. These are like really old school capacitors, or capacitors that you might see in like something really simple like a toaster, for example. A toaster is just a current coming in and there might be some capacitors there. That's how you get, so when the charge is maxed out on the capacitor, then the toaster switches up. That's because of a capacitor. The way it looks on the inside of this is that imagine this being a plate and then there's another plate behind it, and that's what's forming these parallel plates. Here, for example, their parallel plates are going to be round, right? But they're still right next to each other. And because these things are really small, the distance between them is really, really, really small. These ones are a bit special. They're cylindrical, but they still contain parallel plates. And I'm going to bring you to that slide right away, actually. The way you would have it is you would take two flat parallel plates, but they're malleable, and then you fit them in between with another malleable substance, and then you can roll this up together into a cylinder and fit it into that battery shaped thing, and that's how you have a cylindrical capacitor. But in essence, all throughout, those two plates are always going to be parallel. They're going to be separated all throughout by their dielectric. All right, you guys see what I'm saying here? Yeah. Okay. Yeah. So imagine you took a pita bread, right, and you put a layer of salami on it, and you put another piece of pita bread on it, and then you rolled it, right? That's how you would get your parallel plate, the two slices of pita, and the salami would be the dielectric in the middle, and that way you can fit it inside like a wrap, or you can fit it inside a capacitor shell. Okay. So that's what that would look like then. You guys hungry now? Yeah. You don't want the current to pass. So I'll explain that. Don't worry, I'll explain that. Okay. Um, let's talk about really quick. Let's talk about the insulator in between. What's really important about that insulator is that it has to be a polarized molecule making up that insulator. So in this case, you can see that the molecules of the insulator have a positive and a negative end. And when there is no voltage, they're just kind of hanging around, all right, in any random direction. If you apply a voltage, so let's say here you have positive V and here you have minus V, right, then those polarized molecules will all line up together. And that's really, really important too. That's going to be how your capacitor is going to be allowing more charge, all right? But here or not, I will explain how that works in a current first. I just want to do a couple very simple problems with you guys first, and then I'll show you how the capacitor works. Here I have a capacitor that has a charge Q and minus Q. Here I have the same capacitor with charge Q and minus Q on each plate, right? The only difference between these two is that I have a dielectric in the middle of one of them and no dielectric in the middle of the other, all right? And you can see here, the voltage required to reach that same charge difference is lower for B, right? You required less volts to achieve the same charge on the plates as you did compared to the first one, which required more volts to do that. The dielectric made the job of the voltage easier to charge with the same number of charge. And again, I'll explain that in a video very shortly. Let's do a problem real quick. A science fair radio uses a homemade capacitor, right? Actually, before we do that, I'm just going to write down here what the relationships are. Is Q is equal to C times V, and C is equal to K times area divided by distance multiplied by epsilon naught. Those are the two equations I went over in the last few slides. So I have some capacitor with that area, 35 by 35, and it's separated by a sheet that is 0.25 millimeters thick. So if I wanted to calculate capacitance, I would have to use the dielectric value of the piece of paper, the area of the capacitor, which would be 0.35 times 0.35, divided by the distance between them. So if the thickness of the paper is 0.25 millimeters thick, that's pretty much the separation that's going to be from the two capacitors. So this would be 0.002, nope, another zero actually, 0.00025 meters multiplied by epsilon naught. And that should give me my capacitance. Maybe someone can calculate it for me real quick. On your calculator? No. It's 8.85 times 10 to the minus 12. Yes. I don't know. It's not an easy one to remember. It's like coulombs per meters minus 2 over kilograms, something. Yeah. What did you get? Did you get something? No, you didn't? Farad. Okay. 1.6 times 10 to the negative 8 farads. That's the same thing as 16 nanofarads. And in fact, that's pretty much the realistic frame that you're looking at for your own devices. So for example, a camera flash, it's got about 16 nanofarads. It's got actually more like 25 nanofarads for a camera flash. And actually before the school year started, I don't know if I told you guys the story when I got that nasty shock from the camera flash. That was this. That was 16 nanofarads of shock that I got. And it was painful. It was not a walk in the park. I wish I'd never felt that again. I actually kind of scared Tanya. By the way, you guys are going to be doing that next class. And from the what? The flash of a disposable camera. We'll do it safely. And in worst case scenario, it just stings a little bit. But in any case, if you manage to get your hands on a capacitor that's measured in farads, that stuff is dangerous. All right, so you definitely want to stay away from that. If it's 16 nanofarads, so something that's like basically 100 million times weaker than 1 farad is going to hurt. Imagine how much something that's 100 million times stronger is going to hurt. So it holds that much more charge. It's actually deadly at that point. And they don't exist really for consumer use. Like if you go to the Access Electronic and you're trying to make your own circuit or whatever, you won't be able to find that. But they do exist and they're used for bigger things. Yeah. 16 nanofarads means that when it's stored at its maximum with the voltage source or whatever, it's going to hold this charge Q that you can calculate. Yeah, exactly. Let's try example number 2. A 30 nanofarad homemade capacitor is connected to a 25 volt battery. How many charges are held by the capacitor? Well, that one's pretty easy. It's Q is equal to C times V. If Q is equal to C times V, I mean, that's pretty simple at this point, right? So you have 3 times 10 to the negative 8 farads multiplied by 25 volts, 30 nanofarads. So, right, but I put 30, So can someone give me an answer for this? It should be like 7. Exactly. Coulombs. Is that what the question's asking though? Just the charge? It's asking for how many charges. So I'd have to divide this number by 1.6 times 10 to the negative 19 coulombs per charge. Okay. Just be careful with that on the test. Don't make stupid, careless mistakes where I'm asking you for charge and you find me the number of charges or vice versa. I'm not trying to trick you, but if that's what the question asks, you have to answer the question, okay? And I know you know how to do it. Just remember to do it. That's my only advice. Okay? I don't really need a number here because whatever, you just punch it in your calculator. All right, question B. The capacitor remains connected to the battery. It's the same capacitor. Now, except this time, I'm putting a dielectric in there. What is going to happen to the number of charges that it can hold? Is it going to be able to hold more charges? Yes. How many times more charges? 81 times more charges. So in this case, 81 multiplied by 7.5 times 10 to the minus 7 coulombs is going to be the new total charge that I could store in this capacitor. Okay? Can someone do this calculation for me real quick? That divided by, yeah. Can I get a number for this? $6.1 times 10 to that? No, I haven't done it. Minus 5? It's not the number. I didn't give the answer number of charges. I just gave you the charge. You can do the next part, I think. The number of charges, you can do that on your own. Yeah. Okay, C is a little bit more difficult, so we're going to have to watch a video to understand this one. So I'm just going to read it so that you guys keep this in mind. If the capacitor was disconnected from the battery, before the dielectric was inserted, what would happen to the amount of charges and to the voltage applied across? So let's watch the video that has to do with that. I believe that's this one.
Hello, Dejan Nedvilkovski here from howtomechatronics.com. In this tutorial we will learn what capacitor is, how it works, and take a look at some basic application examples. There is almost no circuit which doesn't have a capacitor on it, and along with resistors and inductors, they are the basic passive components that we use in electronics. A capacitor is a device capable of storing energy in a form of electric charge. Compared to a same-size battery, a capacitor can store much smaller amount of energy, around 10,000 times smaller, but useful enough for so many circuit designs. A capacitor is constructed out of two metal plates, separated by an insulating material called dielectric. The plates are conductive and they are usually made of aluminum or other metals, while the dielectric can be made of any kind of insulating material, such as paper, glass, ceramic, or anything that obstructs the flow of the current. The capacitance of a capacitor, measured in farads, is directly proportional to the surface area of the two plates, as well as the permittivity of the dielectric, while the smaller the distance between the plates, the greater the capacitance. That being said, now let's take a look how a capacitor works. First, we can note that a metal typically has an equal amount of positively and negatively charged particles, which means it's electrically neutral. If we connect a power source or a battery to the metal plates of the capacitors, a current will try to flow, or the electrons from the plate connected to the positive lead of the battery will start moving to the plate connected to the negative lead of the battery. However, because of the dielectric between the plates, the electrons won't be able to pass through the capacitor, so they will start accumulating on the plate. After a certain number of electrons accumulated on the plate, the battery will have insufficient energy to push any new electrons to enter the plate because of the repulsion of those electrons which are already there. At this point, the capacitor is actually fully charged. The first plate
has developed a net negative charge and the second plate has developed an equal net positive charge, creating an electric field with an attractive force between them, which holds the charge of the capacitor. Let's take a look how the dielectric can increase the capacitance of a capacitor. A dielectric contains molecules that are polar, which means that they can change their orientation based on the charges of the two plates. So, the molecules align themselves with the electric field in such a way enabling more electrons to be attracted to the negative plate, while repelling more electrons out of the positive plate. So, once the capacitor is fully charged, if we remove the battery, it will hold the electric charge for a long time, acting as energy storage. Now, if we shorten the two ends of the capacitor through a load, a current will start flowing through the load. The accumulated electrons from the first plate will start moving to the second plate until both plates become back again electrically neutral. So that's the basic working principle of a capacitor, and now let's take a look at some application examples. Decoupling capacitors or bypass capacitors are typical example. Decoupling capacitors are often used along with integrated circuits and they are placed between the power source and the ground of the IC. Their job is to filter any noise in the power supply, like voltage ripples which occur when the power supply for a very short period of time drops its voltage, or when a portion of a circuit is switched causing fluctuations in the power supply. At that moment, when the voltage drop occurs, the capacitor will temporarily act as a power supply, bypassing the main power supply. Another typical examples are capacitors used in DC adapters. For converting the AC voltage into a DC voltage, a diode rectifier is usually used, but without the help of capacitors, it won't be able to do the job. The output of a rectifier is a waveform. So, while the output of the rectifier rises, the capacitor charges, and while the output of the rectifier declines, the capacitor discharges, and in that way smooth the DC output. Signal filtering is another application example of capacitors. Because of their specific response time, they are able to block low frequency signals, while allowing higher frequency to pass through. This is used in radio receivers for tuning out undesired frequencies and in crossover circuits inside speakers for separating the low frequencies for the subwoofer and the higher frequencies for the tweeter. Another rather obvious use of capacitors is for energy storage and supply. Although they can store considerably lower energy compared to the same size battery, their lifespan is much better and they are capable of delivering energy much faster, which makes them more suitable for applications where high burst of power is needed. So that would be all for this tutorial, but you can always find more details and efficient energy.
I'll ask you guys some questions here. So you asked this before. Okay, so the electrons flow in this direction to go into this plate. Can they jump over from there to there? Why not? Yeah, there's an insulating substance. The better this insulating substance is, the less it's going to allow. Now, your next lab, the one that's coming up next class for you guys, it's Tuesday, I think. So Tuesday, you guys are going to be working with capacitors. It's a capacitor lab. And you're going to have to be careful. You guys want to bring this as close together as possible. But as soon as it touches, what's going to happen? Then they're going to be charged by contact, right? Remember, that's a way of transferring charge. So if you touch these, then it's just going to become electrically neutral again. What happens if you touch one of these with your hand? Then you're going to ground it and you're going to lose the charge. Okay, so you have to be careful not to touch this with anything. I mean, we're working with really, really, really low capacitance, so you're not even going to feel a shock when you touch this. But what it's going to do, it's going to ruin your results, right? You're just going to have to restart the experiment, right? You definitely don't want to touch this with your hands, and you definitely don't want to touch these two together because you're going to short the current. Now, okay, so the problem said that after it sends this last electron here, why can it not send any more electrons? Yeah. Exactly. Yeah. So once you shove all your electrons here, your battery is only strong enough according to the battery. right? So if you put a stronger battery, then yeah, you can get more charge in there. But with one battery, you can go all the way there, and then at a certain point, you reach the max. Like this battery is just not strong enough to push the electrons in anymore. So at best case scenario, what could the voltage across these two plates be? Exactly. Okay. The voltage across these two plates can never be higher than the voltage of the battery. Okay, that's super duper important. We'll talk about that again when we talk about circuits. It's more important there, but it's also very important there, right? So yeah, so you can't shove in any more electrons because of that. Now, if I were to double the voltage, then yes, I'm gonna get some more energy in order to be able to push those electrons across, and therefore I'll shove more electrons. It's not because there aren't any more electrons left here. It's just that the battery is just not strong enough. Yeah. It's yeah, exactly. In an ideal world, it'll be equal to the battery. In the real world, it's going to be less. Okay, and you guys will see next week when you do your lab, your voltage will be basically zero. It'll be unmeasurable. Now, how does the gonna go ahead a little bit. Here, okay. So here you have your dielectric. That's lining up in this orientation because of your electric field. How is this dielectric, explain to me what he said, how is the dielectric helping you bring more charge? Yeah, more charge than if I did have it. So we said that the voltage can only do so much. The voltage of the battery can only do so much. But why is the dielectric helping? Yeah, so now this dielectric is working together with the batteries. The battery is trying to push this, and the dielectric is also pulling the electrons because of the positive charges that are there. So if the dielectric is better, you can pull in more charges, and your capacity becomes better. Your capacitance or your capacity for more charges becomes higher. Okay? I'll ask a couple more questions. What happens in this state? Open circuit, fully charged capacitor. Okay, so the electrons will stay put. Okay, so this here, because this is pulling each other, the charges actually stay on the plate. I mean, you could short this, and then they'll go zoom, they'll go all the way across, and you'll discharge it back into the other plate. Or you can use a load or whatever, and if you touch this, you'll get the shock. But essentially, there is no charges that can go this way, but they're being attracted towards the positive end. Therefore, the charges are held. All right, this is a huge difference between a battery and a capacitor. Is that a capacitor is going to hold this charge for a long time. The battery will discharge over time. If I were to now connect these two wires, how long would it take for it to discharge? Second, macro, nano, picoseconds. Okay, so fast that you can't even calculate seconds. Okay, so that's another difference with batteries. A battery will produce a current over a long period of time, but capacitor will discharge it like that, right? So let's say you have a 1.5 volt battery, or forget about a 1.5. Let's say a 9 volt battery, those square ones. You guys know what I'm talking about? Have you ever put your tongue on that? And you feel a little stinging? That's 9 volts going slowly into your tongue, right? Imagine you had this 9 volts as a capacitor, and the entire battery discharging a fraction of a second into your tongue. Deadly. Okay, you definitely don't want 9 volt capacitor discharging into your tongue. Okay. Now, what's cool is that as you attach a load, well, now you're completing the circuit, and these electrons have a way of going back home, right? Now these electrons can go back home to where they began, but as they're moving, there is a load there. So on their way home, they're going to light up the light bulb, so they can do some work. In this case, it's a light bulb. In many cases, it could be for whatever reason, for transistors, for processing, for flash of a camera, for whatever it might be. That's when it's doing its job. Okay? Not long at all. Exactly. But one thing that was really cool that they explained, I mean, you might have not have picked it up, but here, sorry, sorry. What's cool here is that if you look, this green thing is the voltage of a power source. So your computer or whatever you're using is not getting a constant voltage, right? And that's really crappy for your device. Your devices won't work properly if it's not getting a constant voltage. But a capacitor, what it's cool is that when the voltage drops, the capacitor compensates by boosting it up so that you're always staying at this constant level. So you don't have drops in voltage. Or similarly,
Supply. Another
if I go here, you can see here, if I have an alternating current, and I make it so that everything is positive, so I take the absolute value of this alternating current, it kind of looks like this. So the voltage is always going up and down, up and down, up and down. Well, that sucks for your device because look at how many times the voltage drops. Voltage drops, the voltage drops. So what a capacitor will do is that during that short period where the voltage drops, your capacitor is discharging. And during that time, between here and here, your voltage is recharging. Because this happens so quickly, your capacitor is constantly charging and discharging to make sure that you get a flattest amount of voltage or the most constant source of voltage possible. Okay? They're hugely important, right? Because the electricity we get from Hydro-Quebec is not that good. I mean, it's good in the sense that we get a lot of it, but it's not a constant voltage source. It's a wave function. Any questions about that? Let's go back and answer those last questions, and then we'll take a break. So here it says, if the capacitor was disconnected from the battery before the dielectric was inserted, what would happen to, one, the amount of charge, and two, to the voltage? Who can tell me that? Say that again? Come on, guys. If I disconnected the battery, does the plate hold its charge? Sure, yeah. It doesn't really, with a dielectric, it doesn't really matter. There's still going to be an electric field, yes, but it's asking about the charges. What did you say? So you guys are saying different things. Who's right? She's saying the charges will go back. You're saying the charges will stay. Ah, okay. But is there an empty space there? It's not likely that the electrons will jump over. I guess both of you would be right in this case. So ideal world, the charges would stay, but because the dielectric is pretty crappy, the charges might probably jump over the bridge. So I'm going to write down, I'll go with Genevieve's answer and say the charges stay on the capacitor. What happens to the voltage? Voltage also doesn't change. Voltage stays the same as the battery. All right. Yep. Yeah, exactly. Before that, they're neutral. I'm going to ask you guys a question before I let you go off on break real quick. If I had, let's say it's connected to some voltage source. Here are my parallel plates. And I shoved as many positive charges as I possibly can here and as many negative charges as I can there, right? And in fact, I overcharged them. And the reason I could do that is because I have my dielectric in the middle. right? And then I removed, so then I disconnected the battery. Then I remove the dielectric. What's going to happen? Is the charges going to stay or are they going to jump across? The extra charges will jump across because remember the capacitance of the capacitors depend on that dielectric. So if you remove the dielectric, the capacity goes down, and that increase that you got from that dielectric, it's going to get discharged, and you're going to be left over with what it would be without the dielectric. Yeah. To discharge, the same speed instantaneously. Okay. When we do circuits, you can put a resistor between the battery and the capacitor. So here's your battery. And here's your resistor. And there you're doing something called an RC circuit. And an RC circuit, it charges more slowly. And you can discharge it more slowly as well. But if there was no resistor there, instantaneous. Okay? Okay, so the plan is that we're done with capacitors. I want you guys to take let's say a 10-minute break, come back at how much time? This class goes until what time? 3:30? Yeah, so take 10 minutes, come back at, like, let's say 21 on this, and then I have review questions for the test that we can do for the rest of the period, okay? Yeah, 10 minutes.
Yeah. Il n'y a pas de batterie, il n'y a pas de dielectric. Mais si on enlève la dielectric, tu viens de dire qu'elle traverse de chaque bord. Les charge.
Si on fait de quoi avant qu'on insère le dielectric va rien faire. Okay? So imagine that this problem has no dielectric at all. Okay? All right? And so you charge it with a battery, and it's gonna get its charge from the battery. Then you remove the battery or you cut the circuit. What happens to the charge? Well, they don't do anything, they just stay like that. That's what a capacitor does. Si je l'ai chargé après, j'ai enlevé le dielectric. Donc j'ai chargé avec le dielectric. Puis après que je l'ai chargé, j'ai enlevé le dielectric. Là, il va y avoir un jump. Exactement.
But what happens to the charges that were inside the dielectric? Like they just go straight to the opposite side and then
There is no charge in the dielectric. The dielectric prevents the charge from jumping across.
But you overcharge the
plates.
The plates.
Right. So what will happen is the plates will now only have a certain capacity for charge, and then that excess is going to jump across.
Okay.
Yeah, because that's going to be the closest point to it. Yeah.
It was 27 lines.
Who submitted the first one?
Him.
And who submitted this one?
Me.
That's the problem.
Okay.
You had to do it. You have the same person has to do it because now it looks like you copied his paper.
Okay, so
Yeah. So it's okay this
It's
time.
alright.
Just make sure you don't do it.
Okay.
Okay, so let's do some review problems. This is purely for the test. The way it's going to work, there's 10 questions here, one per slide. And I'm going to solve one, and then you're going to solve one. And we'll take turns like that, okay? And we have a full hour to do this, so I think we should be able to get through all of them. Some of them are easier than others. In terms of its difficulty compared to that of the test, I would say they're all pretty much the same. The harder problems on the test are going to be harder than all of these. The easier problems on the test are going to be easier than all of these, okay? So there's really a big range. This is more like the middle range, okay? Some of you have asked for hard problems. I'll send one or two. I don't have many hard problems that I can give you without giving away all of my bank of hard problems, but I can send you guys one or two for you to practice with, for you to see how well you know this stuff. Now, because I send you hard problems on electric field, doesn't mean that on the test I'm going to give you a hard problem on electric field. I can give you a hard problem on anything I want. I'm only going to give you a few, so I can't cover everything. Another person asked me, if I do every single problem on the website and I read all my notes, how well could I possibly do on your course? You could do as poor as 2% or as high as 100%. It really is a matter of how well you understand the stuff. Guarantee you there won't be questions that I've asked you before. I'm going to ask you all new questions. So if you've done them all and you're thinking that now I know all the possible questions, nope, you don't, all right? And that's not the way to study anyway. So let's try these. I really want you guys to actively try to solve these, okay? I don't want you to just listen or whatever. Try to think about them. Ask questions if you need to. If you're not interested, this is review. You can leave now if you want. The solid inner shell holds a total of -3 nanocoulomb charges, while the outside sphere holds a surface density of that. Determine the amount of charges on the outer shell. All right, that's pretty easy. Look at my sigma here. Is it uniform or non-uniform? It's uniform. So if it's uniform, I can just find Q by multiplying sigma by the area. There too. All right. So if I were to do it now, it would be -5.57 times 10 to the -8 coulombs per meters squared, multiplied by the area, which would be, what's the area of a circle? A sphere, sorry, is it a sphere? Yeah, sphere. Of a sphere. 4 pi r squared. I'm going to change color so you guys can see better. All right. Can someone give me an answer for that? Andre? -7 nanocoulombs. Okay? Or -7 times 10 to the -9 coulomb. Perfect. So that would be the answer for A. B, find the electric potential at a point located 2 centimeters outside of the outer shell of this sphere. So remember, if we use Gauss's law, we know that if we look outside of a sphere, we can treat the sphere as a point charge. So we can say that voltage is equal to just KQ over R. That's a point, that's how you measure the voltage of a point charge. So let's do this. K is 9 times 10 to the 9. What's my charge? I just found the outer one, but what's my charge? What's the charge of my entire sphere? Which would be -10 times 10 to the -9 coulombs. And then what's my R? It's tricky. 12, exactly. It's 12. It's not 2, it's 12. The reason is because if we're treating my sphere as a point charge, then you need to take the distance as if it were a point charge as well. So you measure it from the center of the sphere, which would be 12 centimeters or 0.12 meters. I'm just going to do this in my head real quick. Yeah, easy peasy, 750 volts. I did this before. Okay? So in this question, does it tell me it's a conducting or an insulating sphere? It doesn't say. So there is a mistake in the problem, and I don't tell you because I'm going to ask you to draw the electric fields now. It doesn't tell you what the electric field looks like. It doesn't tell you if it's insulating or non-insulating. So I can't tell you what it looks like in that black area. Let's say if it was a conducting sphere, what would the electric field look like inside the black area? It would be nothing because the charges are located on the outside. If it were a totally negatively charged, uniformly charged insulating sphere, what would it look like? What? Charges everywhere, they're negative, what would the electric field look like? Outside in though, because it's negative. I have to mention to you what it is, otherwise. So I'm just going to show it to you because there's something to show. What about on the outside of that inner sphere? What are the charges in the inside? If I took a Gaussian surface here, right? What are the charges inside? Negative or positive? Negative. So the electric field lines should go towards the middle. Yeah. Very good. If I took a Gaussian surface on the outside, what would the electric field be on the outside? Whoa. Oh, no. What would the electric field be on the outside? Towards the middle. What's going to be my total charge of my sphere? Minus 10, all right? So don't forget to add those charges. If it were positive and negative, some of them might cancel each other out and it might become positive. In this case, they're both negative, so the overall electric field is going to be contributed from negative charges. So my arrows will all be pointing inwards from everywhere. This is what your eyes will look like after you've done all of your semester. Nope, nope. I'm only asking for the direction. But if I were to ask you, is it stronger closer to the surface or away from it? Whether it's negative or positive, it doesn't matter. Not even that. I'm talking about if you were to compare here versus like up here, which one's going to have a stronger electric field? Closer to it, because you're assuming it's going to be a point charge when you're outside of it, so it's inversely proportional to R squared. The potential, no, even the potential decreases as you go far away, because that's KQ over R. If you're outside of the sphere. If you're inside of the sphere, no. Perfect. Linear? Nope. That's a good question. If I were to graph the inside of the sphere between the black sphere and the edge of the outer sphere, what would it look like? Would my electric field, okay, so let's say I took this Gaussian surface versus this Gaussian surface, which one would have a stronger electric field? Hello? Yeah, the smaller one would have a stronger electric field. So as you go out, the electric field is getting weaker and weaker until you hit the next surface. Okay, so it's going to decrease as a proportion of 1 over R squared. That one will increase depending on how uniformly charged the charge is. Okay, let's do question 2. This one you guys are doing on your own. I'm answering it here, but don't look at my answer. Do it on your own. Don't look at my answer. There's no point in looking at the answer. You can only see this problem once without seeing the answer, right? Once you see the answer, you can't unsee the answer. It's like spoilers. Can I freeze it? I'll just wait. Okay, I'm going to start adding my solution now. So if you want to stop looking, you can stop looking. Yeah. Go for it. Okay, moving on to the next question. Two positive charges are separated by a distance of 300 meters. Explain. We were supposed to do that one on your own. The explanation is right there. You can check it out after class. It's a proportion, essentially. You got the same answer? There are a couple ways of doing it. Okay, this one we'll do together. So two charges are separated by a distance of 300 meters, and there's a space in between these two that's going to be if you put a charge there, and you don't know what the charge is, if you put a charge there, the total charge, or the total force rather, is going to be 0. So let's draw a little drawing. So there's my little drawing, and there is a point somewhere here where if I put a Q, the forces are 0. Now, what is the distance between here and here? That's R. And if that's R, if that distance is R, what's the distance between Q and here? 300 minus R. Very good. So now if I add the two forces, well, hold on. There's two positive charges, so the forces are going to oppose each other, right? Okay, good. So if I had to do that, so I would say that K plus multiplied by 8.0 times 10 to the minus 3 coulombs times Q divided by R squared minus, because the force of the other one's going to go in the opposite direction, K times 2 times 10 to the minus 3 coulombs multiplied by Q over 300 minus R, all that squared. All that, when you add them together, it should give me 0. Okay, I set it up. Essentially, if you want to stop paying attention now, it's just algebra to solve the rest. I'll do it, but it's just algebra. So try to follow along. My k, oh, no, I can divide everywhere by k, because on one side it's 0. I can divide every side by q, because again, it's 0 on the other side. So I'm left with, and if I bring this expression, if I bring this on that side, I'm going to be left with 8.0 times 10 to the minus 3 over r squared is equal to 2 times 10 to the minus 3 over 300 minus r squared. All right? And we could also square root both sides to get rid of those squares. So I'm going to square root both sides, and I'm going to work up here. So it's going to be the square root of 8.0 times 10 to the minus 3 divided by r is equal to the square root of 2 times 10 to the minus 3 over 300 minus r. Now I'm going to cross multiply like that. And what I'm going to get is the square root of 8.0 times 10 to the minus 3 times 300 minus the square root of 8 times 10 to the minus 3 times r is equal to the square root of 2 times 10 to the minus 3, sorry, I'm running out of space, times r. And I bring all the r's to the same side, so I'm going to be left with the square root of 8 times 10 to the minus 3, minus here, multiplied by 300 is equal to r multiplied by root 2 times 10 to the minus 3 plus root 8 times 10 to the minus 3. And then I divide both sides by that so I can solve for r. And I know this from the other classes because I've done this 3 times already. The answer here is 200 meters. Yep. It doesn't matter what you put there. What does it mean? What's happening at that point there? It doesn't matter what I put there, the electric field is 0. Yeah. The truth is there is another answer. But because it's a multiple choice, we solved for the one that I knew was going to be the right answer. So when I did this here, when I did the square root, you had to also write the negative. You have to put a minus sign there to get the other answer. Okay, moving on. This one you're doing on your own. So again, don't look up if you don't want to see the answers. I'll give you guys a few seconds to read and process. I'm going to start writing the answers. You should do them all. The ones that you know how to draw, you should draw. Okay, that was question 4. I'm moving on to question 5. Yeah. You mean over here? Where? Which part are you talking about? The positive and negative? Oh, yeah. If you were, yeah, you can go like that. Yeah. Okay. Number 5. This one has integrals in it, so if you're having trouble with that, maybe it's time to pay attention. So a non-uniform volume charge distribution for a non-conducting sphere of radius r is modeled by rho is equal to 4r plus 3, where r is the distance from the center of the sphere. Question A, calculate the charge on the sphere. So I know that if I have a sphere, let me just change my color again. If I have a sphere with a radius r, I can break this up into a lot of little spheres. And each one of these little spheres is going to have a radius little r. Okay? And if I took the charge of just one of these spheres, so dq, of just one of those spheres, then I can use my charge distribution and multiply it by the volume of that small sphere. All right? And those are hollow spheres, right? Not solid spheres. So how do you find the area, or sorry, the volume of a hollow sphere? Surface area? What? That's the charge. That's the charge. That's nothing to do with the volume. So what's the volume of a hollow sphere, guys? The surface times the thickness. What's the thickness? dr, exactly. Okay. So now if I want the full charge, Q, I can do the integral of that from the center, which is a radius of 0, to the edge, which is which is a radius of 2 centimeters, of all that, which is, I'm going to take out the constants, 4 pi. I'm going to distribute to R3, so it's going to be 4 R3 minus plus 3 R2 dr. And that's a pretty straightforward integral. So I just solved my integral. We did the physics part. That was the hard part, is setting up the integral. After that, it's just math. All right, you have a question? Can someone give me an answer for this? So punching it in. Times pi, you said? Could you multiply the pi in just so I can have a number? So essentially 1 if we're doing sig figs. To the minus 4 or minus 3? Cool. Okay. Yeah, so and then to find a number of charges, I would divide this by 1.6 times 10 to the negative 19 coulombs per charge. I'm not going to do it, but you should do it. Okay, so for B, calculate the voltage of distance from 3 centimeters. Well, we've done this already. You treat it as a point charge because you're outside of the sphere, and the voltage is going to be equal to K Q over R, so 9 times 10 to the 9, multiplied by Q, which is 1 times 10 to the minus 4, divided by R, which is 3 centimeters, plus the radius of the sphere itself, so 5 centimeters. And that should give you some answer that's going to be equal to, like, what is that? 18, 1.8 times 10 to the 5 or so. Maybe you guys can confirm. 10 to the 6, maybe? To the 7. To the 7 volts. Okay? Any questions? Oh, we have tons of time. Question 6. You guys do this one. I have a follow-up question for you. So once you determine which one belongs for the situation at an electric field level, then identify which one belongs to the situation on an electric potential level. So which one is for electric field, which one's for electric potential? Yeah, but you already made it not nice with this, so you might as well continue. You can keep it as like a that if you want, but if you're gonna go all the way to this step, you might as well go to the next step. Okay. Did I make a mistake? So the integral of 4r to the 3. Right?
Okay. Because I took it out as an integral and
I didn't because I knew that was coming. But you can't actually take it out because the other one didn't have a 4. You can't take out a 4 if the other one has a 3 next to it.
but it's separate, it's separate.
Oh, yeah. Okay, so for question number 6, the answer is, to your chagrin, E. Why? Your butt flesh. Okay, if this one had arrows, if the one on the bottom right had arrows, then it would be right. But it's no arrows, so therefore there's none of them are correct. That's sneaky. But the other one has an answer. If I were to ask you about potential or equipotential lines, what would it look like? 3? Everyone agree with 3? Really? That's 3. So if I were to draw the electric field lines perpendicular, okay, so that was this problem here. Let's do question 7 together. Here are some charges. Determine which ones are positive and which ones are negative. So how do we do that? Equipotential lines, are they going to be positive near the positive charge? Yes. So there's a positive 5 and it's decreasing as it's going away. So this one must be positive. This one's decreasing as you get closer to it. And this one's decreasing as you get closer to it. So therefore, those two are negative. All right. Draw the electric field lines. Yes, Sammy? So here it's the closest one is 5. Then the second closest one is 4 and then 3. So it's decreasing as you're going away from it. That means it's increasing as you're getting closer to it. So if it's increasing as you're getting closer to it, that means it's positive. It's the opposite for the other two. It's going to be, they're negative numbers. Exactly. Yes, they would, but not from the bottom two charges. So it should look something like, this, like this, like this. Like that. Okay? See, an electron is moved from point A to point C. How much work is done? Well, we have to remember that work is equal to voltage or delta V multiplied by Q. So work is equal to Q delta V. Well, that's pretty easy. The delta V between A and C is what? 0. No work is done if you're going from an equipotential point to another equipotential point. E. Identify a region of weak electric field. So let me just keep drawing my electric field lines. I didn't do D, eh? I wrote the answer in the wrong spot. So work is equal to Q delta V. That's equal to 0 joules. A proton is released at point C. So over here, where is it going to go? Towards the bottom? It's a proton, so it's going to go towards a negative charge. So it's going to go in this direction. So it's going to go towards Q3. Guys at the back, please. Thank you. E, identify where there's an area of weak electric field. Where? Here? Here? The electric field there is what? There is an electric field. If there were only two charges, you'd be right. But there is this charge up here that's going to act on it as well. It's weak. You're right. It is a weak point. It's not strong. Another way of looking at it is how? How do you determine strength of electric field? Not equipotential lines, but the actual electric field lines. But what about the electric field lines? The distance between them. So if you were to draw all of these, I mean, you could make it so that there is distance here. But if you look here, there's a lot of lines coming out of those. There's a lot of lines coming out of those. But around here, the density of electric field lines is lower. So the electric field strength in those areas is lower. And in F, finally, identify a region of high potential. Where would that be? High potential. It has to be positive. So none of those really strong ones near Q1 and Q3 really matter. The answer would have to be near Q2. Or just on the surface of Q2, the potential is going to be very, very, very high. Positive high. Okay, question 8, you guys do on your own. Let's go. Consider uniform electric field. What is the electric flux of this field? I is that unit vector I, like an ijk. What is the electric flux of this field to one side of a cube having a side of more? Oh, this is a good question. I like this one. Well, it's telling you that it's telling you the electric field direction of the area. None of my answers match. That's weird. Did I do my calculation wrong? 0.02 times 0.2 times 0.2? Ah. So what's the answer now? All right. I forgot it was in kilonewtons. Yep. When it's not totally like like if area and the electric field didn't hit it at a perpendicular angle, or if the normal vector from the area and the electric field were not parallel. Because it says that the plane is parallel to the xy of or the yz of the axis. So if you remember in linear algebra, this is I hat, this is J hat, and this is K hat. You've never seen that? Okay. Huh? I thought. It's cosine of 0 because the surface area has its own vector, remember. Exactly. Yeah. All right, that's question 8. Let me ask you a follow-up question. What if my plane was parallel to the XZ axis? 0. Okay, thank you. Moving on. Question 9. A hollow metal sphere has a total charge of, guys at the back, please, I'm not going to ask you again. A hollow metal sphere has a total charge of 100 microcoulomb. If the radius of the sphere is 50 centimeters and the electric field intensity at a distance of 3 meters from the surface of the sphere is approximately, we could treat this as a point charge. So I don't need to do all that Gauss's law stuff for this one. I just need to do kq over r squared is equal to E. So 9 times 10 to the 9 multiplied by the charge, which is 100 times 10 to the minus 6 coulombs, divided by the distance, which is 3.5 squared, because remember it's the distance to the center. And that should give me my electric field strength at that far away. Yeah. Yep. It would just be radially outwards because it's. Can I get a number here? How much? To the 4? Is that right? So I guess D would be the closest one to it. Okay. Last question. A spherical shell of radius of 9 centimeters carries a uniform charge density of 9 nanocoulombs per meter squared. What do you notice about that charge density? Uniform or not uniform? Uniform, good. Make sure you ask yourself that question each time, okay? The electric field at R is equal to 16 centimeters. Is approximately, okay, so now we got to do. It's the same thing. It's kq over r squared. Yeah. When you're using Gauss's law, you can consider a point charge if you're far or outside of a spherical object. You can be far from any object or anywhere outside of a spherical object. Uniform, then you'd have to do an integral to find the charge. Okay. Then you would just plug that charge into there, and that's it. Yes. Exactly. But this one is saying the R is 16 centimeters, so that's assuming it's already from the center. This is pretty good. With the other two classes, we only got to number 7. You guys are the first to get it here, and we still have some time to spare. You guys are just great. No doubt about it. What's that? What's the answer that we that you get out of it if you do the calculation? What did you get? So I'm getting different and conflicting answers. Are you making sure everything is square? It's a exactly. What did you get, Gabrielle? Do I have another bonus? I don't have another bonus. All right, guys, that's it for today. You're done 12 minutes early. Have a lovely afternoon. See you guys on Tuesday. Again, make those appointments quick. They're filling up. Yeah.